Good morning. Today I would like to present our work promising compilation to ARMv8 POP. Even though we don't have weak memory in our title, we, as the previous work, also working on weak memory. And actually it's a work about correctness of compilation from the promising semantics, which was mentioned in the last slide of the of Jan Oliver talks, to a memory model of ARMv8. So I should thank Jan Oliver for nice introduction for weak memory. So I'll add a little bit about that. So we all know that modern compilers and CPUs are optimizing. They have different features which are intended to increase performance of a target program. And most of them prove to be correct for single-threaded programs. However, they may introduce new behaviors in concurrent setting, which can't be explained by interleaving execution of threads. Such behaviors are usually called weak behaviors. In the previous talk, there was a store buffer example. Here, I'll add a little bit to the picture, and we'll consider load buffer example. So here we have two threads. In each thread, the first instruction is a load, and the second one is a store to a different location. We assume that both locations x and y are initialized by zeros, and the weak behavior of this program is a equals to 1 and b equals to 1 at the end of execution of this program. It's obvious that we can't get this behavior in interleaving execution of the program, as if we execute this program interleavingly, then either the first instruction from the first thread, which is a read, or the first instruction from the second thread executes first, so we get either a equals to 0 or b equals to 0 at the end of execution. Memory model is semantics of programming language with concurrency, and we call it a weak one if it allows behaviors which can't be explained by interleaving execution of threads. In the recent past, industry and academia developed a number of memory models for both hardware and software. There are memory models for mainstream computer architectures, including x86 Power and ARM. There are also memory models for mainstream languages such as C, C++, and Java. However, it's well known that these memory models have different flaws, including out-of-thin-air values and unsoundness of some commonly used optimizations. So there is an auspicious attempt to solve these problems, which was published at POPL this year, Promising Semantics. And an essential thing to do about new model is to prove compilation correctness to mainstream architectures. So in the original paper, authors proved the correctness of compilation to x86 and Power. However, they didn't for ARM. And unfortunately, the same technique used for x86 and Power is not applicable for ARM, as ARM shows very weak behaviors. So the goal of current work is to prove correctness of compilation from the promising semantics to ARM POP. So the result of our work is proof of compilation correctness for a subset of promising semantics. The subset comprises relaxed loads and stores and release and acquire fences. Also, we proved a number of auxiliary results about the ARM model itself, which we believe might be reused in other proofs about the model and connecting it to other memory models. So, to make a brief introduction to both Promise and ARM memory models, I'll consider load buffering example in both of them. So, how can they get load buffering in ARM? ARM memory model has so-called storage subsystem, which mimics hierarchical structure of memory in modern CPUs. There is buffers, and there is memory. Buffers are lists of memory requests to the storage, and memory is just a map from locations to values. So ARM is allowed to execute instructions out of order. Via gray boxes we denote instructions which are not executed by ARM yet. So to get load buffering behavior, the second thread can issue a read request to the storage subsystem, then issue a write request to the storage subsystem. As we see, these two are two different locations, so they are independent, and that's why the storage subsystem may reorder them, and if it does, then after that the write request is eventually propagated to memory, so we get this one. After that, the first thread can issue a write request, which is eventually propagated to memory as well. So after that, the read request from the second thread might be propagated to memory and then satisfied there, assigning 1 to B. So now there is only one instruction left to be executed. It's a read instruction from the first thread. So the first thread issues a read request to the storage subsystem, which is eventually satisfied with 1. So we get a result A equals to 1, B equals to 1. How can they get the same behavior in the settings of the promise memory model? In the promise, memory is a set of messages. Each message comprises a location, a value, and a timestamp. Timestamps are used to induce a total order on writes to messages to a specific location. Also, each thread has so-called views, which were presented by Jan Oliver in the previous talk. Unlike the ARM memory model, the promise machine is very limited in out-of-order execution, and each specific moment of promise execution, each thread can either execute an instruction which is pointed by its program counter or to promise a write. So here the first thread promised to write 1 to location Y. After that, it adds a message to memory, making it observable to read from 4 other threads. To get the interesting behavior, now the write thread might be executed in order. First, we assign 1 to B, and then add a corresponding message to memory. Now the left thread can read from this newly added message, assigning 1 to A, and after that fulfill its promise. So this is how we get the same behavior in promise machine. There were 2 main obstacles in proving correctness of compilation from the promise machine to the ARM one. First of all, the promise is very, as I said, is limited in out-of-order execution. So the promise machine cannot follow directly steps of the ARM machine, and also there is timestamps in the promise machine which totally orders writes to a specific location, but there is nothing like that during execution in the ARM, so that's the problem. To solve these problems, we have 2 main ingredients in our proof. First of them is logging simulation, and the second one is ARM plus timestamps. Actually, it's an intermediate machine, a version of ARM machine which assigns timestamps at the moment it issues write request to the storage. I'll start with logging simulation. So let's take a look at the following example. Suppose we have a part of the program and it's partially executed by ARM, and here the first instruction is fully executed by ARM, the third one is partially executed by ARM, and the second and the fourth one are not executed by ARM yet. So, and suppose that the promise machine proceeded through the prefix of the program which is fully executed by ARM, so its program counter points to the second instruction. As in all simulation proofs, we have a simulation relation. Actually, in our case, it consists of 2 parts. And at this point, the first one holds. After that, the ARM machine can partially execute the second instruction and fulfill it and complete it. After that, the second part of simulation relation holds, which means that the promise machine has to make a step, and after it makes a step, now it's once again in the state that is waiting for other steps of the ARM machine. So after that, ARM can send a write request to the storage subsystem, and if the promise machine does nothing at this step, then simulation relation doesn't hold. To restore it, the promise machine has to promise the corresponding write, and after it does so, once again, it's in waiting state. Actually, at this point, we have to promise a message with some timestamp, and we'll discuss how to do that in the remainder of the talk. So after that, there is only one instruction left to be executed for the ARM machine, so it finishes executing it, and after that, promise machine can proceed through these two instructions. So the second part is the intermediate machine ARM plus timestamps or ARM plus tau. In the ARM setting, suppose we have such a program. At some point, ARM machine can issue two write requests to the same location in the program, and the storage subsystem can either propagate the left request first or the second one. Depending on that, the final order of writes to location X depends on that. And as I said in our simulation proof, we have to promise writes at the same time our machine issues them to the storage. So we have to assign some timestamp, and actually assigning timestamps induce some order. And as it's order defined earlier, we have to do something in the ARM. So actually we decided to determine the order beforehand. So we introduced these ARM plus timestamps machine. And at the moment it issues write request to the storage, it assigns some timestamps to them. So ARM plus timestamp machine now is allowed to to propagate these write requests to the common buffer, but it's not allowed to propagate this one to the common buffer, as there is another write request to the same location with a smaller timestamp, which is in sibling buffer. So the bird's eye view of our proof is following. First, we introduce an intermediate machine. As I said, it's more restricted in a sense that it disallows some propagations in the storage subsystem. So we have to show that even though there is such restrictions, the set of behaviors for every program is the same. So we prove equivalence between them. And after that, we show logging simulation between the promise machine and the ARM one. More details might be found in our proof, or in our paper, sorry. So the future work is to cover other features of the promise machine, to mechanize proof in ECOOP, and also recently the new model for ARM was proposed. So it seems stronger than the one we were working on. So we believe that the proof for this model will be easier. So that's it. Thank you.
Well, if it's only me who has questions, I won't keep you from lunch.
I'm a bit, I would like some help to understand a bit better about the timestamps. You say that the timestamps are given in advance, and I can imagine that that you just flip a coin and give timestamps, but that only works up to a certain extent, because there must be some dependency on program execution. So what is the mechanism that gives the timestamps?
Okay, actually,
or is there a concept of valid timestamps allocation, that an allocation of timestamps is valid with respect to some execution or something?
Mm-hmm. First of all, if we are speaking about our machine, then it's one answer, and if we are speaking about promise machine, it's another one. So I guess we are speaking about ARM. Okay, so I'll explain it here. At the final state of ARM execution, every write request is propagated to main memory. So I haven't said that, but actually the main memory is not just a function from locations to values, but actually it's some graph having dependencies between write requests, and actually there is a total order on write request at the end of ARM execution. So there is one. So the way we introduced timestamps, and actually we said that if there is some total order at the end of execution, then we can assign timestamps according to this order during execution. So if we have a whole execution, then we can assign timestamps during the execution. So there is no magic about that.
So there is no allocation before execution. You just leave the timestamps in order to explain.
You mean allocation of locations?
You have to see the future.
Yeah, that's true.
So I understood how you solved the problem about here with the writes, but you also said that that reads can be reordered in ARM, and that was another difference with the promise model.
Yeah.
Was that resolved somehow by the lagging simulation?
Yes.
I didn't quite make that connection. Could you maybe clarify that?
Okay. In our lagging simulation, the promise machine executes only instructions which are fully executed by ARM and which are preceded by fully executed instructions. And these reads, which are executed by ARM after program counter, they somehow like internal steps in simulation. So we don't have to follow them directly, but at some point we will, and actually it's encoded in our simulation relation that we can make the same steps, but after at some point.
Okay, so how does your simulation account for the fact that a reordered read could read a different value than if they proceeded in order?
Sorry, could you repeat, please?
If the read is reordered, it could read a different value, right?
Yeah, but actually it's covered by the promise semantics itself. Like there, as Jan Oliver explained, there is these views and these things. And actually, for example, at this moment of time, write thread has to read from write to location X, which is not older than the one with timestamp 0. And for the same for Y, but it also can read from the newer ones, so like here, so it increases its view. So if reads are reordered, then it may affect which message we are reading in the promise machine, but in our simulation relation, we state the fact that it's allowed to read the same write which was read by the ARM machine.
Super, thank you.
All right, thank you. Don't go away quite yet. More announcements.